Hey everyone, and welcome to this explainer. Today, we're stepping into the totally fascinating world of fluid dynamics. You can think of this as a bit of a masterclass, where we're going to investigate those hidden, invisible forces that literally surround us every single day. I'm absolutely thrilled to be your guide on this, because we're going to break down some brilliant engineering concepts and make them incredibly easy to understand. By the time we wrap up, I promise you're going to look at pipes, pumps, and even the weather in a completely different way.
I want you to start by just pondering this question for a second. How exactly do you measure the invisible? I mean, we live at the bottom of a literal ocean of air, and fluids are constantly rushing through pipes in our homes and cities under tremendous forces. But we can't actually see pressure itself, right? We can't hold it in our hands. What we can do, however, is measure its physical impact on the world around it. And engineers have designed some incredibly clever ways to do exactly that, basically by making this invisible force do some heavy lifting for us.
Okay, let's dive right into this. The key to our whole investigation today lies in a deceptively simple device, the manometer. It's technically defined as the simplest pressure measuring device used for measuring low pressure or pressure differences using fluid mechanics. Before we start upgrading our tools to measure microscopic changes, we've got to establish this baseline. You see, a manometer isn't relying on digital sensors or complicated finicky electronics. It relies purely on the basic physical laws of nature to give us incredibly accurate readings.
So here's our roadmap for today's explainer. First, we'll cover the invisible force. Second, the classic U-tube. Third, the inclined manometer. Fourth, the differential manometer. And finally, we'll wrap up with a lecturous cheat sheet so you can lock it all in.
Starting off with part 1, the invisible force.
To measure pressure, we actually need it to do physical work for us, like moving a fluid. It really all boils down to this one fundamental principle. Pressure differences push liquids. If you have high pressure on one side of a tube and low pressure on the exact opposite side, the liquid inside is going to get pushed toward the low pressure side until the forces finally balance out. It's like a microscopic tug-of-war. By simply measuring the physical distance that the liquid moved, we successfully capture and quantify that invisible force. Every single manometer we're looking at today relies on this beautiful, fundamental physics concept of balancing forces.
Moving on to section 2, the classic U-tube.
Now, what's really interesting here is the physical setup. Notice the fluid sitting at the bottom of that U-shaped glass tube. That is our manometric fluid, and it's usually something much heavier than whatever fluid is flowing through the pipe. Mercury is a classic example. This heavy manometric fluid acts as a physical barrier. It's basically a liquid wall sitting right between the two pressures we're trying to measure, which we're calling P1 and P2.
Let's walk through this like a physical story. Step 1. The higher pressure, let's say P1, pushes down really hard on the liquid in limb 1. Step 2, because fluids are largely incompressible, that heavy manometric fluid has nowhere to go but to get displaced. It gets pushed down on one side and forced up on the other, creating a very distinct height difference we call H. Step 3 is the math. The change in pressure, delta P, simply equals that height difference H multiplied by the difference in density between our heavy manometric fluid, rho m, and our flowing fluid, rho, all multiplied by gravity, G. So just by reading that height H off a simple ruler, you can perfectly calculate the pressure difference. It's actually genius.
To help you lock this in, here is your very first memorization tip. I want you to think of the U in U-tube as standing for universal. The U-tube is your universal heavy lifter. When you're dealing with standard everyday pressure differences in a chemical plant or a commercial water pipe, you grab the U-tube. It's the absolute most common and robust tool for the job.
That brings us to section 3, the inclined manometer.
But hey, what happens when our universal heavy lifter just isn't quite sensitive enough? We have to upgrade our toolkit for a new kind of challenge. Imagine you're trying to measure the draft of air in a building's ventilation duct. The pressure change is so incredibly slight that it might only move the fluid in a vertical U-tube by a single millimeter. I mean, a 1 millimeter change is practically invisible to the naked eye, right? Especially if you're trying to take a reading in a busy, poorly lit industrial setting. So, how on earth do we solve this?
Well, engineers came up with a brilliant solution. Notice how instead of a perfectly vertical tube, one arm of the manometer is tilted at a very specific angle, which we label alpha. Usually this is a pretty shallow tilt of just 5 to 10 degrees from the horizontal. And why do we do this? Because if fluid drops vertically by just 1 tiny millimeter in that chamber on the left, it physically has to travel 7 to 10 millimeters along that tilted glass tube on the right just to reach the exact same vertical depth.
We are literally stretching a tiny, basically invisible vertical drop into a long, highly visible movement along the glass.
So the crucial point here is how this alters our math just a tiny bit. Because we're now reading the distance along the incline, which we call r, we have to use some basic trigonometry to find our true vertical height, h. Height h simply equals r multiplied by the sine of our angle alpha. That gives us our modified equation. And here's your memory trick for this one. When you think of an inclined tube, I want you to picture a playground slide. You slide down the sine wave. That instantly reminds you that the inclined manometer requires that sine alpha calculation to find the true vertical pressure head.
Next up, Section 4, the Differential Manometer.
Let's move to something even more precise. What if we need extreme precision, or we need to actively compare two different pipes? Visually, this setup looks a bit like our standard U-tube, but notice those enlarged chambers at the top, the reservoirs. Now, it's also worth noting that differential manometers can actually be built upside down. We call that an inverted U-tube manometer. The inverted version is perfect for measuring liquid flows, usually by trapping a lighter manometric gas or fluid up at the top. But whether it's upright or inverted, the really cool thing is that this manometer uses two entirely different immiscible liquids, labeled here as fluid B and fluid C, sitting right there interacting with each other.
To make this magic work, engineers carefully choose two liquids that have nearly identical densities. For example, they might use paraffin oil and industrial alcohol. Because their densities are so incredibly close to one another, they don't mix easily. Instead, they create a very sharp, highly sensitive boundary layer, an interface, right where they meet inside the tube.
Because those densities, rho C and rho B, are nearly identical, it takes a massive shift in the liquid level H just to balance out even a microscopic change in pressure between the two reservoirs. If you look at our equation, it relies on subtracting one density from the other, rho C minus rho B. If those two numbers are super close, the difference is just a tiny fraction, which means H has to be huge to make up for it. Your memorization tip here is simple. Differential equals dueling densities. The magic happens right at that battleground where those two similar densities meet.
Finally, Section 5, the lecturer's cheat sheet.
We have definitely covered a lot of ground today, and this brilliantly illustrates your entire toolkit at a single glance. If you're dealing with standard pressure drops across a pipe, you want the universal heavy lifter, the U-tube. For small, tricky differences that are hard to read with the naked eye, you grab the inclined manometer, and you remember to slide down the sine wave. And finally, if you need extreme precision, you break out the differential manometer, whether that's upright or an inverted U-tube, relying on those dueling densities to multiply your reading into something clearly visible.
I want to leave you with this final thought. You are now equipped with the exact same fundamental knowledge that professional engineers use to design fluid systems all over the globe. So next time you feel a strong gust of wind against your face, or you turn on a faucet and watch the water rush out, ask yourself, which of these tools would you reach for to measure that invisible force? Thank you so much for joining me for this explainer. I really hope you feel empowered to look at the world around you with the sharp analytical eyes of an engineer. Keep learning, keep questioning everything, and I'll see you in the next one.